Welcome to our demonstration of the PG-KLEE toolset. In this video, we will provide a quick overview of the progressive symbolic execution technique and perform a walkthrough of a PG-KLEE application on an experiment in our ICSE 18 paper. The approach to an input generation task should be selected with consideration of the requirements of its application. Applications such as bug detection may need soundness to limit false positives and may tend towards the left side of this spectrum of unconstrained state. In contrast, other tasks favor completeness over soundness. For example, populating a model with samples of possible behavior for matching against future observed behavior can be tolerant of infeasible behaviors in the model, but cannot match missing behavior. We describe one such example in our demo paper, with further detail in the ICSE 18 paper. With this context in mind, we develop progressive symbolic execution. PSE over-approximates program behavior by symbolically executing increasingly small fragments of the original program until a given coverage goal is met. It begins conservatively at the top of this table and then descends to more aggressive strategies. Classic symbolic execution is unlikely to find inputs for all program paths, but PSE will find inputs for the missing path segments, including a few infeasible ones. These inputs can then be used to execute program fragments for segment model population. We'll now demonstrate how this works in practice by performing the input generation and replay steps from the ZAPI replace experiment. We start by identifying the path segments that constitute our coverage goal. We select a set of program points with instrumentation called markers. A marker-to-marker path is a path through the static control flow graph from a marker to an adjacent marker. Our coverage goal is then to find inputs to the program or fragments thereof to exercise all marker-to-marker paths in the program. For these experiments, we inserted markers into the entrance and exit of functions, loop headers, and go-to jump targets. Though not covered here, we ran KLEE with symbolic program inputs for 60 minutes for empirical comparison to PG-KLEE. We execute PG-KLEE to generate replay cases for each function in the program. Before symbolically executing the SD-close function, PG-KLEE will unconstrain global variables and create symbolic input arguments. If all of the marker-to-marker paths have not been covered by the specified 1-minute timeout, PG-KLEE will unconstrain local function state and begin from interior basic blocks that can reach the remaining marker-to-marker paths. In this case, we see that PG-KLEE found 2 replay cases that cover all 4 marker-to-marker paths through SD-close. Now, running PG-KLEE manually over each function is tedious, so we provide a Python script driver, run PSE, that performs a top-down traversal of the program call graph and invokes PG-KLEE on each function with uncovered marker-to-marker paths. In the example shown here, we have chosen timeouts to rapidly progress to additional unconstrained state. This allows PG-KLEE to quickly discover replay cases. This configuration will tend to find short replay fragments. If our application prefers longer path segments with more of the original program execution context, we can increase the amount of time allocated to symbolic execution with input state only. This example requires slightly over 50 minutes to complete. Note that the final coverage is the same either way. The gen replay script invokes a scaffolding generator that takes the original source static analysis data and PG-KLEE generated replay cases and produces a program that combines all of the fragments and generated input data for replay on a target device. The resulting program is configured with CMake and compiled. Executing the built host replay program iterates through and replays each of the cases. In the example shown, 140 replay cases completed and none faulted. The replays can then be validated for divergence from the replay cases. The resulting statistics show that PG-KLEE did indeed find feasible marker-to-marker paths missed by other input generation techniques. If your input generation application can tolerate some infeasible behavior, increasing unconstrained state can lead to increased coverage with fewer resources. Thanks for your interest in our tool, PG-KLEE.